Welcome, and thank you for joining us in this third podcast with Dr. Nis Rahman, President, Chief Technical Officer, and inventor of T-Ray terahertz-based technologies for Applied Research and Photonics, Inc., ARP. My name is John Mahoney, President of C4 Technology, a sales and consulting company servicing the semiconductor industry. Today, we're discussing gallium nitride, GaN, and as related to semiconductor processing, mainly for power and optoelectronic devices. While GaN devices continue to dominate alongside silicon carbide, GaN processing presents multiple challenges. We discuss some of these process challenges in this first in a multi-episode series on GaN. Dr. Rahman, welcome.
Thank you very much. Thank you for inviting me.
You're welcome. Dr. Rahman, if you could please get into a little bit of detail of T-Ray, why GaN is important, what some of its process challenges are, and how ARP T-Ray can offer solutions.
Thank you very much. And again, thank you for arranging the podcast. I have a small presentation. Maybe I can share that with you and with the podcast audience. So let me share my screen. Where did it go? Here we go. Share this one. Share. All right, and let me also go to the presentation mode and all right. So are you able to see my screen?
Perfectly.
Wonderful. So this, as you indicated, the gallium nitride is becoming very important. So we have a little bit of work in that area. I'm going to talk about the lattice damage under electric stress. And probably not today, but we'll also talk about the high electron mobility transistor made from GaN. And of course, our tool is always terahertz. That's our main tool. I am Nis Rahman, and you're most welcome to ask your audience to contact for any questions or follow-up. So, so I will give you a little bit brief background of our company and the technology before I go to the GaN, but specific ones. So we have been in business for a long time. And a lot of things has been grown in-house very slowly over a long period of time. We have been fortunate to draw attention from government laboratories as well as universities and some industry leaders. But we are still, as you know, we are still trying to get a good commercial footing of our technology. So we have been able to achieve lattice resolution imaging since 2018 via some project. So here is the terahertz where it lies on the spectrum. The electromagnetic spectrum shows that there is to be terahertz gap between far infrared and microwave. And then Austin switch was the state of the art at that time, and which we have been able to find another mechanism called dendrimer dipole excitation. And that's how we generate T-Ray. And as is on the lower right, you see a picture of Don Altamalia and myself. Don Altamalia is the pioneer and known as the father of dendrimer. And I have the opportunity still working with him today, but started in the 90s. I have been working on dendrimer, and then we found a way of engineering the dendrimer to make high electro-optic coefficient material or high Chi2 material from dendrimer, and then generate terahertz radiation out of that the power and bandwidth can be tunable. We can tune that. So Don published a very important paper in the Nanotechnology Horizon journal, and he called this as the Rahman-Tamalia effect of generating this terahertz radiation. So without going into the details, let's focus on imaging first. The most important thing about terahertz imaging, the way we do is we replace the camera or a charge coupled device CCD, or in general a focal plane array, by a nanoscanner. So the main rationale is that, first off, when we use a camera, its ability to resolve any object depends on the visible light as well as the underlying CCD that records the image. So if the CCD has 100 megapixel ability, that's the best we can get out of it. And that is always a handicap or bottleneck, because sometimes we need very fast, very high resolution, sometimes we need very low resolution, depending on the sample. So we found that if we have a nanoscanner, as you see on the lower left corner, then we don't need the CCD or camera anymore. We can generate the reflected intensity matrix by scanning an object, and we scan in real volume. Therefore, we can generate a volume image. And then we can have, smaller resolution, bigger resolution, and so on and so forth. So some of the things we have discussed before, but most importantly, it gives a volume image and the layer by layer analysis ability in any of the three axes. So we can slice a volume image along the x-axis or y-axis or z-axis, and how many slices we can get, there is no limit. It can be less than angstrom, it can be millimeter, and in between anything. So then how does it compare with the other existing techniques? There are some pros and there are some cons. The main disadvantage is that it's a two-step process. First, we have to scan and then image generation. So therefore, the imaging is not in real time. And so that is a small, disadvantage that we have to go through compared to the advantages on the left side. As you can see, no camera, no CCD, resolution chosen by user, not CCD limited. Resolution range from macro to sub-angstrom. And the samples are scanned, no sample preparation necessary. It also doesn't matter what size and shape of the sample is. It can scan just about any size, any state of the sample, liquid, solid, or gaseous. Volume image, as I said, layer by layer. And measurement of size and thickness and any other metrology function that is needed for semiconductors are available here. It's a tabletop system, and it has all the equivalent functionalities of an AFM, an SEM, and a TEM combined. So only difficulty is that it cannot do the elemental analysis with an extra probe like SEM does. This is meant for molecular analysis that can be done with the spectrometer, as well as can be imaged. And it's not a handheld device yet. A probe probably can be developed to make it a handheld device at a later time. With that, let's move on to GaN, or gallium nitride. Our efforts are mostly to see the latest. Gallium nitride is supposed to be used at high electric field conditions and other harsh environment conditions. That is the importance of gallium nitride. It can take more load. It can be used in outer space, in harsh radiation conditions, and so on and so forth. So we focus first on the lattice damage, if we can quantify that. And at a later time, we'll come to then time domain deep level spectroscopy to see below the surface how the spectral signature changes. And then high electron mobility transistor made out of GaN and its frequency domain characterization. So two basic samples. One is the gallium nitride film that I'm going to talk today. And then on the deep level time domain spectroscopy on film, as well as on high electron mobility transistor, will come at a later time.
Okay, thank you.
Feel free to ask any questions you may have up until now. So as an introduction now, because the demand for energy efficient and high performance electric field devices continue to grow, gallium nitride transistors are poised to play a pivotal role in various industries, including telecommunications, aerospace, automobiles, and renewable energy. All of these are very important application of the gallium nitride as a semiconductor. And then our tool, as I said, is T-ray. T-ray is a new modality of cameraless imaging. It does volume and layer by layer, as I mentioned. It also has both reflection mode imaging as well as transmission mode imaging ability. And T-ray is the main attraction is that it can see more. Not only what camera misses, whatever the camera misses, T-ray does not miss, and I will show you some comparison. But it also can see smaller features, and it can see much more clearly than anything else compared to be it X-ray, be it optical, be it AFM, etc. It can see much more clearly both the material, the lattice, and their interfaces. So the main issues in GaN are that despite all of the advantages we mentioned so far, the widespread adoption of gallium nitride technology faces few challenges, particularly the manufacturing complexity and establishing its reliability, as well as thermal and high electric field management still remain the issue. And growing the single crystal is very complex process. So the boules, they cannot grow a much bigger boule, although so many techniques are there like hydride vapor phase epitaxy, which is the most commonly used technique. Ammonothermal growth is another one, melt solution growth, and sodium flux method. These are all effective, but it's like, silicon boule, you can grow 3 meters long. So in one run, you can get 3,000 or 5,000 wafer, depending on its thickness. That's not the case for gallium nitride. The gallium, up until now, although they have been able to grow 150 millimeter diameter boule, their thickness is still, the three thicknesses that has been reported in the literature is 2.6 millimeter, 5.8 millimeter, and 6.3 millimeter thick boule. So in 6.3 millimeter, again, very top and very bottom are probably not useful. So from the middle, you can get only a few wafer per boule. So far, the gallium nitride technology is still dependent on silicon wafer by epitaxy technique. So that's one of the things that the industry is trying to get over. So in our case, we are using terahertz instrument, and here is the picture. On the right side, a tabletop system where there's a main box in the middle, and on the left side, there is a nano scanner, and on the right side, the computer screen. And then on the lower bottom, excuse me, the details of the nano scanner is given here. Basically, it's an X, Y, and Z axis. And there is an optical circuit, or terahertz circuit, I should say, where the T-ray beam is delivered by a fiber into that circuit. Then the circuit scans the wafer when the wafer is mounted on a on a mount which remains stationary. So once the scanning is done, then the data is stored in the reflection matrix, and computer then does the analysis or create the image and make measurements.
And does Dr. Rahman, if I could interrupt just
Please.
briefly, does the fiber coupled beam delivery system, does that provide some flexibility for the system? And if so, what is the flexibility that?
Right. It certainly does provide a lot of flexibility. First of all, it always ensures the vertical incidence on a sample. The samples doesn't have to be vertical all the time. It can be vertical, it can be horizontal, it can be at any other angle as well. If I have a non-uniform shaped sample, I can make sure the vertical incidence, because the T-ray circuitry, fiber delivered circuitry, is can be mounted on a rotary stage, and then the rotary stage can be used to point the beam at a given angle, whatever angle, and we have the software to determine the right angle for vertical incidence.
Okay.
And also the other advantage is the stand-off distance. A lot of times it's a non-contact system, so sample can be closer or further, and that can be accommodated and adjusted by the same arrangement as well. So it does have multiple advantages.
But within reason, you can mount the circuitry closer or further away from the sample and still focus in on where you want to focus.
Absolutely.
Right, perfect. Thank you.
Sure. So yeah, that's a very good point. And here are some of the results of the gallium nitride film. First, we're talking about the film. As you can see on the upper left, a little bit broken piece of a silicon wafer on which the yellow color marks the GaN film. So these are the GaN film. This is a little one, this is a little one over here. And these GaN films are deposited on this wafer, which is a silicon wafer, and then was subjected to high electric field stress. And that experiment was not done by us. We got the sample as is after they performed the high electric field experiment. And the point was, when they look at this spot under light microscope, they have seen these dark spots here and there. So the question is, how did it affect the lattice structure of the film itself? So, as you can see, if you put it under, let's say you cut a small piece and polish it to electron transparency and put it in TEM, that will give you a frozen in time image of the whole thing, whole thickness, as thick as smallest as thickness as you can get to make it electron transparent. So in our case, we have an advantage is that we can then scan through the surface and see not only on the top, but also the bottom, and I'm sorry. So this image, this three-dimensional image, and then top surface is on the upper right, which is a red color. And you can see the perfect lattice on the bottom. And then the sum of them, some of the surfaces are smudged, the drastic deterioration of the surface of the lattice. So this kind of investigation we can do only with T-ray. X-ray and any other technique is not very effective in this kind of investigation. So if we take that volume image and we can then extract the layers, here I am showing two layers on XZ plane along the y-axis. So I have one slice here, one slice there. And as you see, if you go through the whole structure, the arrangement, lattice arrangement changes, and we are able to quantify that. So this is only a 2 micron by 2 micron by 2 micron structure, and then within that 2 micron thickness, on the z-axis is this one is the z-axis. As you can see, some layerification, for the lack of a better term, has happened. And then if we take only one of the slices, we can see the details, morphology across the thickness. And then we can, what we call is a graphical analysis. If we can do the graphical analysis, then we can measure the thicknesses of each of the lattice plane that has distorted or remained good. So each can be quantified. And I guess the only other thing I'm going to show here is a lattice image of a different sample whereby we can measure the lattice parameters as well. And with that, I think, and the interface, of course, I have talked about it before, but interfaces can be characterized because of the lattice scale resolution imaging. With that, I will stop here today, and I'll open the floor for your questions.
Very good. Thank you. Sure. Well, very good overview. Thank you very much. Next time we are going to talk about the terahertz time domain spectroscopy a little bit.
Absolutely.
And that will be related to, which is a key feature of the TerraSpectra tools.
Mm-hmm.
And you'll have some discussion of time domain spectroscopy and imaging on the GaN subject.
Yes,
okay.
Of course.
Well, Dr. Rahman, I believe that you've covered quite a bit for today's session. We could go on and on, of course. You did a very good job of explaining the difference between some of the optical techniques, why the TerraSpectra T-ray is advantageous, and certainly scanning electron microscopy and TEM, AFM as well. Of course, all non-contact, non-destruct, and non-ionizing. So you can reuse samples for further testing if necessary. And I believe that's very important to get a continuity of where problems and when problems are occurring, not only in process, but after devices are completed and put under power and so forth. So, well, very good. Well, Dr. Rahman, if you have no other input for today's session, we'll go ahead and wrap it up, and we'll reconvene at another time, and we'll discuss not only gallium nitride, but you've done a lot of work on silicon carbide, another power device substrate. And we'll get back into discussing whole wafer profile mapping and 100% die sort analysis,
Yeah.
which is very critical to the industry. Well, thank you very much for joining us today, Dr. Rahman. It's been very informative, and we look forward to speaking with you again.
Wonderful. Thank you, John. And we have lot to discuss, and I really can't appreciate enough all your effort. Thank you.
You're welcome.